Welcome to the Deep Dive. Today our mission is to really dig into a big challenge in managing the world's oceans. How do we look after fish stocks when, honestly, we often have hardly any data?
Yeah, it's a huge gap, a really significant one. We think, the majority of fish stocks that are commercially fished worldwide just don't have those formal assessments, no reference points.
Because we often don't know their status, whether they're healthy or, well, in trouble.
Exactly. We're flying blind in many cases. And this is despite laws in places like the EU, the US, Australia, New Zealand.
Right, laws that say all exploited stocks need to be managed. You can't just shrug and say status unknown. That's not really management, is it?
It really isn't. And that's precisely why we're doing this deep dive today into a really important paper from 2016. It's titled Estimating Fisheries Reference Points from Catch and Resilience, and the lead author is Froese, working with several colleagues.
And this paper tried something, well, pretty ambitious. Figuring out those critical numbers, maximum sustainable yield, MSY, and the original population size, K, for stocks where we have very little information.
It was ambitious but necessary. They were essentially trying to find a shortcut, asking what's the absolute minimum information we need to go from we have no idea to having a decent science-based management target.
Okay, so let's break down how they did it. They came up with two methods, CMSY and BSM. But for managers really starved of data, CMSY seems like the main event here.
That's right. CMSY, it stands for Monte Carlo method. It's designed specifically for those low data situations. You only need three things, basically.
Okay, what are they?
The catch history, how much has been caught over time, then a general sense of the species' resilience. Does it bounce back quickly or slowly?
And the third?
And finally, just a broad qualitative idea of whether the stock was, say, high or low at the beginning and end of that catch record.
Okay, minimal indeed. And then there's BSM.
BSM, yeah. That's the Bayesian state space implementation of the Schaefer production model. Think of it as the benchmark they used.
More data hungry, I assume?
A bit, yes. It still needs the catch history, but it also needs some kind of abundance data over time, either actual biomass estimates or, more typically, catch per unit of effort, CPUE.
So, because BSM uses more data, they treated its results as kind of the truth to check if CMSY was giving sensible answers.
Exactly. It acted as the internal check on the minimal approach.
Now, both methods rely on this thing called the Schaefer production model. Can you unpack that a bit? What's the core idea?
Sure. It's actually a pretty simple concept for modeling how a fish population changes. Imagine you've got a stock of fish. Its size, or biomass, depends on just a few key things.
Okay.
First, how many fish are there right now, the current biomass? Second, how fast can they reproduce and grow? That's the intrinsic rate of increase. We call it R.
Got it. Growth rate.
Third, the environment's carrying capacity, CARE. That's the maximum size the stock could reach if nobody was fishing it. And fourth, well, how many fish are being taken out the catch, Carrie?
So population change is basically growth, determined by R and K, minus the fish we catch.
You've got it. And the really neat part is the relationship to maximum sustainable yield, MSY. That's the biggest catch you can take year after year without depleting the stock long term.
And where does that happen?
It happens when the stock is exactly half its maximum size, so K divided by 2. Growth is slow when the stock is tiny, and it's slow again when it's near the maximum K because of, limited resources. The fastest growth is right in the middle.
Ah, the sweet spot.
Precisely. And mathematically, this means MSY equals R times K divided by 4. So if you can estimate R and K, you immediately get MSY.
Which is the whole point of CMSY.
Right.
To work backwards from just the catch data and those few priors to estimate R and K and therefore MSY.
That's the game. CMSY uses that very basic info to estimate R, K, MSY, and also track how the relative biomass and fishing pressure have changed over time.
Okay, this is where it gets interesting. How does CMSY possibly find the right R and K just from catch data? Surely there could be loads of different combinations of R and K that could explain the same catch history.
That's the clever bit, the Monte Carlo approach. It doesn't solve it like a math equation. Instead, it uses computing power to basically sift through possibilities and throw out the ones that don't make sense.
How does it do that?
It runs thousands, maybe millions, of simulations. Each time, it picks a random pair of R and K values. Then it calculates what the biomass levels must have been year by year to allow the recorded catches to happen with that specific R and K.
And what makes a pair viable or not? How does it filter them?
Two main rules. First, the calculated biomass can never drop to 0 or below. Obvious, right? You can't catch fish that aren't there.
Makes sense.
Second, The whole biomass trajectory it calculates has to fit with those rough starting and ending biomass levels the manager provided. If the manager said the stock was low at the end, the trajectory has to end low.
Okay, so it's a filtering process based on biological reality and the manager's initial qualitative guess.
Exactly. And when you plot all the RK pairs that pass the filter, you see this characteristic shape, often called the RK triangle, when plotted in log space.
But I imagine that triangle still covers a wide range of possibilities. It shows the uncertainty, right?
It absolutely does. It highlights that ambiguity. A catch history could be from a huge stock that grows very slowly, low R, high K, that's one part of the triangle.
Yeah.
Or it could be from a smaller stock that's really productive and bounces back fast, high R, low K, that's another part. The data limits the possibilities, but there's still a range.
So how does CMSY pick the most likely answer from within that triangle? Doesn't just averaging all possibilities wash things out?
This is a key difference from some older methods. Older approaches might have just taken the average of all viable pairs, which often gave wishy-washy results. CMSY takes a different tack.
Which is,
It reasons that R is the maximum potential growth rate. So the most biologically plausible answer should be found near the tip of that viable triangle, representing the highest possible R values that are still consistent with the data, paired with the corresponding smallest viable K. It focuses the search right there.
interesting. So getting those initial priors, the input assumptions right, is really crucial for guiding that Monte Carlo search. Let's talk about those three inputs again. The prior for R, the growth rate.
Right, the prior comes from general biological knowledge, often using the resilience categories from fish base, very low, low, medium, high resilience.
So the manager picks a category based on the species.
Yeah, and that category gives the model a broad starting range for R. Say, for a high resilience species, maybe R is somewhere between 0.6 and 1.5. It just stops the model from testing completely unrealistic growth rates.
Okay. And the prior for K, the carrying capacity.
That one's based more on logic from the catches themselves. The absolute minimum K has to be bigger than the biggest catch ever recorded.
Because you can't catch more fish in 1 year than existed in the first place.
Exactly. If the peak catch was 100,000 tons, K must have been larger than that, possibly much larger, depending on their value assumed. It sets a logical floor.
But that third one, the biomass status prior, still feels like the trickiest. If I'm a manager with almost no data, how do I make even a rough guess about whether the stock was high or low decades ago, or even now?
That is the biggest challenge, and the authors are upfront about it. It does require some expertise, some qualitative judgment. The manager gives broad ranges like low might be 140% of K, medium 20-60%, high 50-90%.
What if the guess is just wrong?
Well, the good thing about the filtering process is that if the initial guess is way off, the model often just won't find any arc pairs that work with the catch data. It hits a dead end.
So it forces you to reconsider your assumption. It acts as a kind of check.
Sort of, yeah. It constrains the possibilities. It's not perfect, but it helps.
Okay, moving on. The paper also addressed a big problem with older, simpler models, especially for stocks that were already heavily fished down.
Yes, this was a really important improvement. It's about incorporating a more realistic stock recruitment relationship. Think of it like a hockey stick model for recruitment.
What do you mean?
Well, older models, like the basic Schaefer model, often implicitly assumed that even if you fish the adult stock down really low, the number of new young fish coming into the population recruitment stays high.
Which isn't very realistic, is it? Fewer adults usually means fewer babies.
Exactly. So managers might have gotten advice suggesting a stock could bounce back quickly even when it was on its knees. This paper builds in a mechanism where recruitment, and therefore the overall productivity drops sharply if the stock biomass falls below a critical point.
What's the threshold they used?
They set it at 0.25 times K, which is actually half the biomass level needed for MSY, BAMDB. Below that, the model assumes productivity tanks. It makes the advice much more cautious and realistic for depleted stocks.
Okay, that sounds crucial. Now, the validation, did these methods actually work? They tested them against simulations first, right? Where they knew the real answers.
They did, against 48 simulated stocks, and the results were pretty encouraging. Both CMSY and the benchmark BSM performed well.
How well?
For key things like R, K, and MSY, the true value from the simulation fell within the 95% confidence range of the CMSY estimate, most of the time somewhere between 75% and 96%, depending on the parameter.
So the minimal data approach could actually recover the known dynamics pretty effectively.
It showed the potential, yes. Established the basic reliability.
And then the real test, comparing CMSY to stocks that did have full, expensive assessments.
Right, against 128 fully assessed stocks. Here, they use the results from their own BSM method, which uses more data as the comparison point.
And how did CMSY stack up?
Remarkably well. For RK and MSY, the estimates from the minimal CMSY method were not significantly different from the BSM estimates in 76% of those stocks.
Wow, 3/4 of the time, the minimal approach gave basically the same answer as the more data-intensive one. That's
Yeah.
quite something.
It really is. It suggests that for many stocks, you can get statistically sound estimates with much less data than previously thought.
And was it even better for the stocks that were truly data-limited? The ones that only had CPUE data, not full biomass assessments.
Even better, yeah. For those 28 stocks, CMSY and BSM agreed in 89% of cases. And importantly, this held true across a real mix of fish types, bottom dwellers, open ocean fish, deep sea species, and regions, like the Pacific, Atlantic, Med. It suggests the methods are pretty broadly applicable.
Okay, but let's be balanced. No model's perfect. What are the limitations? You mentioned the resilience priors from FishBase didn't always work straight out of the box.
That's true. They work for most, about 88% of the stocks. But for the other 12%, things like surmullet or haddock in some areas, they found they had to manually tweak the resilience category.
Meaning an expert had to step in and say, no, based on what we know locally, this species is probably low resilience here, not medium.
Exactly. It highlights that while the math is powerful, you still need that local expert knowledge to sometimes guide the initial assumptions. You can't just blindly plug and play.
And what about that sensitivity to the final biomass prior, the manager's guess about the stock's current state? You said that was maybe the shakiest input.
It was definitely the most sensitive. The study found that for about a third, 34% of the real stocks they looked at, the initial guess for the final biomass status had to be corrected to actually match the available abundance data.
So what does that tell us?
It tells us that the model really relies on the manager having a reasonably good, even if just qualitative sense of whether the stock is currently in bad shape, okay shape, or good shape. If that endpoint guess is completely wrong, the model might throw out the correct RK solution because it doesn't fit that incorrect final status assumption.
Okay. So if managers start using these tools, CMSY and BSM, what's the big message for how they should actually manage the fishery? If it spits out an MSY number, should they aim right for it?
No, definitely not. And that's probably the single most critical management takeaway from the paper. The analysis produces these helpful status graphs, showing biomass relative to BIMZ, fishing pressure relative to the rate that produces MSY.
Like the Baltic brill example they used.
Exactly. For a stock like that, which was depleted, the advice is clear. Keep catches low. Let the stock recover back up to the BIMZ level first.
And then what? Once it's recovered, aim for MSY then.
Still no. Even then, the recommendation is to manage catches somewhere near the lower confidence limit of the estimated MSY. Not the main estimate, the lower bound. Be cautious.
Aim below the maximal.
Okay.
Sounds familiar. Didn't the authors connect this back to older warnings?
They did. They specifically mentioned the FAO warning from way back in 1983.
What did it say?
That trying to hit MSY on the nose often leads to wild swings, unpredictability, and potentially stock crashes. This study basically provided hard data confirming that risk. They looked at the history of the 156 fully assessed stocks and found that a shocking 92% of them had, at some point, seen catches exceed their estimated MSY level.
Wow. 92% overshot the supposed maximum.
Yeah. And the consequence. Nearly 60%. 58% of those stocks ended up with biomass levels below BMZ. The data is pretty clear. If you aim for the absolute maximum target, you're very likely to go over it and deplete the stock.
So wrapping this up, it feels like Froese and colleagues really delivered something significant here. These tools, CMSY and BSM, they seem like validated practical ways to finally get a handle on all those fisheries currently labeled status unknown.
I think that's fair. They provide a scientifically robust way forward using minimal data. It gives management bodies the tools they need to meet their legal obligations for all stocks.
So the science is there.
The science is there. The methods work. The really big question now, the provocative thought for you listening, is a policy one. Can management bodies globally actually take this evidence on board? Can they shift away from the allure of targeting MSY, which the data shows is risky, and consistently manage fisheries more cautiously, aiming below MSY for safer, more stable, and ultimately more productive fisheries in the long run?
A critical question indeed. Now you are well informed. We'll catch you next time for the next deep dive.